yesterday, some people are still have to come. So for the initial greetings, we have the pleasure to have Professor Martinelli, who is the director of CISA and one of our sponsors. So be aware. Okay, thank you.
CISA also sponsoring this meeting, so
yes,
welcome.
Yes,
I know that with my research funds, and the reason of the support is clearly because this is a very good initiative, because it comes from the young people, so the people that will be the researchers and the teachers, the professor of tomorrow, hopefully.
Tomorrow, the day after tomorrow.
No, it's important also that you meet at this stage of your career, because it's a way also to create a network that will be important in the future. And also the fact that it's not a workshop on a single subject. It mixes together several physics aspects. So that also, I hope, is also fruitful for interdisciplinary initiative and further collaboration in the future. So welcome to CISA. Unfortunately, I cannot say because sometimes I come from a physics workshop. So I spent 2 days in London.
So you are ready, no?
No, this year is a very important year. It's the 50th anniversary of the discovery of CP violation in physics, which was one of the most fundamental discoveries in the 20th century. So, but I cannot give more than 2 days to physics and act as director, but good work and good prosecution of your activities.
Thank you. Okay, so it's a pleasure to have you here in CISA. Welcome also on the organizer side. So we put together some numbers because we are very proud of our short but meaningful history. Because this is the 5th event. We started in 2008. We did 3 events in Rome. Then last year, this year, we are here in CISA. We have been growing. Okay, I'm not sure if I should say this. It's not all the participants are here yet, but okay, we should be 60 people here. So we grew from last year of 20% because we are physicists, so we love percentages. So the event has a multidisciplinary aim. So we are glad to have had during the years people from astrophysics, theoretical physics, particle physics, condensed soft matter, biological physics, medical physics, preservation of cultural assets. We've had a lot of variety, a lot of contributions, and a lot of interesting science. And this year we had too many applications, literally too many to fit in the talks and poster presentations. So we are glad that the people manifested so significant interest in our event that started basically between friends. People said, yeah, let's plan a meeting between us. Okay, and now this year we got applications from India, South Africa, Ireland, Canada, no, in Canada maybe not, I'm wrong, France, Switzerland, United Kingdom. It's 30 institutions globally and 10 from abroad, which sent applications for the meeting, so we can do nothing but be glad of this result. To add to the already very nice bunch of activities that we carried out during these years. This year we also have a workshop about science communication, organized in collaboration with Medlab and with Simona Cerrato, that will be staged this afternoon. And so this broadens the interest of the young researcher meeting, not only in science done by young people at the beginning of their careers, but also looking at how to give back this science to the community of the general public. So how to talk about our results to people that are actually funding their research. So a way to integrate science in the social context of the city and of the nation. So this being said, Let's start with the boring stuff. So I remind that the talks will be of 20 minutes plus 5 minutes for questions. There will be a sign raised when 5 minutes are left and one other sign when 1 minute is left. After that, we will kill you with no remorse. There is a live streaming going on. So the good region is, I think, from here and here to here. So if you are very shy, you can move out and only your slides will be visible. But I don't recommend this. So you can stand here. I think that a pointer is going to be brought in seconds. Marco, di Stefano, pointer? Oh, we already have the pointer. This is faster than light 3. So, beautiful pointer. Okay, I think that we are ready to start. Enjoy the meeting. Okay, so we'd like to call the first speaker. Okay, our first speaker is Paolo Brunello from the University of Pavia, Italy, and let me grab the microphone.
Okay.
So Paolo will talk us about searches for direct stop production within the Atlas experiment.
In this talk, I speak about searches for direct stop production within the Atlas experiment at LHC. I'll start with a brief introduction to supersymmetry. After, I present a couple of data searches in this field, and at the end, I will present a summary of the most recent results. So, let's start with a brief theoretical introduction about supersymmetry. The theory that actually gives the best description of fundamental interactions in energy physics is a standard model. However, from several indications, seems that this model should be extended in order to describe some physics phenomena, like dark matter, and also to solve some issues like the so-called naturalness problem of the theory. What is, in particular, this problem? It's a problem related to the divergent quantum correction of the Higgs boson mass. In fact, if you write down the correction at higher order in perturbation theory of the Higgs boson mass, you see that the various terms depends on a parameter that is called lambda in this slide, that represent the scale of validity of your theory. For example, for lambda equal to TV, you can evaluate the contribution of the various terms, and you see that you have very big contributions that balance each other to obtain a final value for the Higgs mass that is very small, but different from zero. Really, you want usually to set lambda not 10 TeV like here, but 10 at 18 GeV. So this contribution will be very, very, very huge compared to the final Higgs mass value. So seems not natural, seems that there is not a deep physical motivation for the cancellation of so huge contribution to make a so small final value. So this is one of the most discussed problems of the standard model related to supersymmetry. Why? Because supersymmetry can give us a motivation for the cancellation of these divergences. And this motivation is asymmetry, called supersymmetry. The supersymmetry is a relation from both massive scalars and fermions that, and in particular, the symmetry turns a bosonic state into a fermionic state. This is called the superpartner of the original particles, because so supersymmetry duplicates the standard model spectrum. So for standard model, you have quarks, leptons, and gauge bosons. With supersymmetry, you have also quarks, leptons, and bosons. So the duplication of the spectra is the effect of this new symmetry of this theory. In particular, to allow the divergences cancellation, the mass of these new particles should be of the same order of magnitudes of the standard model particles. But there is a problem, because we haven't found any of these supersymmetric particles with the same mass of the standard model particles. We don't have a bottom quark with the same mass of the bottom quark. So the mass symmetry of this theory is broken. The question now is, where are those new particles? How we can find them? The key point is that the Higgs boson exists, and its mass has a finite value that we know experimentally. And the main motivation for this new theory is that there is these divergence cancellations that give us a finite value theoretically for the Higgs mass. So what is the minimum possible light supersymmetric spectrum that stabilizes these divergences? We should have, in particular, the stop quark, that is the guys that we speak about in this talk, and also some lighter particles that are the xenos, that are the mix of other two particles that are charginos and neutralinos. So a brief parenthesis now about how we do a data analysis in high energy physics. Usually we predict the standard model background expectation using Monte Carlo simulations. This simulation also simulates all the standard model processes, the interaction with the matter, and the detector response. So all the known physics within Atlas. In particular, in this plot, in red and violet, you can see the Monte Carlo background expectation for this process. So X in a couple of Z, it goes in for leptons. Also, we simulate a hypothetical new signal. In this case, the new signal was the Higgs boson, this peak. After, you compare experimental data with background only or background plus signal. And with a statistic treatment, you decide which of the two hypotheses has the better agreement with the data. In this case, we have a clear peak here, so you say we have a Higgs boson. Another ingredient is that in supersymmetry we can't find a peak clear as that, because background is much bigger than a signal. So we need some variables to discriminate background from signal, and so to maximize the signal to background ratio. One of these variables could be the so-called MT2. In this example, in this plot, you see that the standard model background, that are all those colorated, has a very clear cutoff here, while signal has a contribution to higher energies. So if you select in your analysis only the events that are here, with a value of MT2 upper than 1000 GV, you maximize your significance. So now that we know how to study these, how to perform a data analysis and what particle we want to study, we need to establish where find stop, in which mass range. The idea is that in this analysis that I will present in the following slide, the stop will decay into a chargino and neutralino, so the two particles that for the naturalness problem should be lighter than stop. You can do various hypotheses on the mass stop. For example, you can say that the stop has a mass higher than the top mass, so the stop to top decay is allowed. In particular, we focus on this intermediate region where the stop has mass in this region. This is not a little complicated plot because it's a three-dimensional phase space where your free parameters are the stop, chargino, neutralino masses that are our free, not known masses. In this case, so the stop decays into chargino plus a big quark, and the chargino decays into a neutralino through a W bosons that decays into electrons and neutrinos. So this is the decay chain that we are looking for. This is another way to view this decay chain. So maybe it's more familiar for a lot of us. So the stop decays into a B quark plus a chargino, and the chargino decays into a W boson plus a neutralino. The W decays into electrons and a neutrino. This analysis, called leptonic MT2 analysis, MT2 is the main variable to select our signal bands. In particular, we do several cuts, several selections on this variable to maximize the signal to background ratio in various regions of the stop mass. Another ingredient in that analysis is the normalization of the background, because you are not sure if your Monte Carlo is simulating the background with the correct yields. So you try to find a region dominated by background with no signal, and here you normalize the background to signal. This is a way to minimize the systematic uncertainty on this contribution. This is an example. Here you can find that the background is dominated by the Z events, by particular ZZ or W plus Z production. So here you normalize background to data. Another important thing is that in what way we can visualize the portion of phase space that is excluded or not by the experiment. So how you can say here could be present a stop, or here the stop can't be. You represent usually this in a stop neutralino masses plane. For example, if you have a stop, you produce a lot of stop mass point to fill this grid, and you say here, for example, stop of 4000 GV and neutralino of 1000 GV. This point is excluded. So using the experimental data and with the full statistical treatment, you say here the stop can't exist. Maybe can exist here. This is these kind of plots are used a lot in this analysis, in particular for different hypotheses of stop chargino and neutralino masses. And I press, I skip a little. So another possibility in study searches is that the leptons are lighter than quarks. If that scenario is allowed, you can have a decay of stops into the leptons, in particular into tau leptons. In these searches, we are looking for the stop that decay into a big quark, a neutrino, and a tau lepton. That decays into a tau and to another supersymmetric particles that is called gravitino. So in this scenario, the main backgrounds and also the selection are similar to the previous data analysis that we have shown. In particular, the key variables is MP2. We can see here a similar plot of the previous, but within the stop tau mass plane. Here you can exclude a large phase space portion across the diagonal using two mass regions. So using different cuts, two bunches of cuts that are selected to maximize the significance here, so for signal region number 1, or here for signal region number 2. So now a brief summary of all the stop results. So now we have a general idea in how a stop searches could be performed. And the most significant plot probably is that. Now we are looking in the stop neutralino mass plane. Several analyses, a lot of analyses have been performed in this plane. And a lot of portion of this plane has been excluded. So what this plot says to us is that a stop with mass here is not possible. We have data that exclude this hypothesis. And while a stop with mass of, for example, 5000 GV with a neutralino of 4000 GV, so here, could be allowed, but is not actually in the range of capabilities of our experiment. So, in conclusion, what is the key of this kind of plot of these searches? The key is that after the first bunch of LHC data, the supersymmetry has moved from the theory that seems to be the most favored beyond standard model candidates to solve the standard model problem to a theory in danger of extinction, because a lot of the phase space accessible to the experiment has been eroded, has been excluded by experimental data. However, we have a lot of phase space that is not being studied already. And probably a clarification of this situation, a definitive word about that will be given to us after the next LHC run.
Okay, does someone have questions for Paolo? I have a question. So, I don't know much about particle physics and possibly even less about theoretical physics. But what I know is that a boson usually mediates something. So, since supersymmetry should transform the leptons into supersymmetric patterns bosons, does this mean that we have a lot of forces lurking around that are mediated by, I don't know, a supersymmetric pattern of a vector?
You have a duplication of the spectrum, but and so we have the 2 times the force carriers of the standard model. We have the standard model bosons, so W, Z, so on, and also the supersymmetric partners of these bosons. So this is the table. And also, for example, the supersymmetric partner of the X, so the xenos. This was your question.
Okay, more questions? Don't be shy. He's here for you. Okay, perfect. What if, I mean, you mentioned how you subtract the background, right? So,
Yes.
and what if there is something, I don't know, some other effect that you didn't account for? I mean, I'm thinking about, for example, background coming for gravitational waves in the big interferometers. You have the noise from the movement of the Earth. And how do you know that you already excluded any other, I don't know, interaction or cosmic rays that come into your detector?
Initially, you do a cosmic ray background measurement, and so you know if in this phase space portion, cosmic ray could be relevant for the background or not. Usually, is not, for example, cosmic ray is not a relevant background. The standard way is to test all the Monte Carlo, all the simulation of background that you have, so for all the standard model processes, and you see what are relevant and what not.
Okay, if there are no questions, let's thank Paolo again. Next speaker is Luca Agostino from APC Paris. Luca will speak us about the Laguna LBNO physics potential for long baseline perturbations.
So, good morning everybody. Thank you very much to the organizers for this opportunity. I apologize for this loss of voice. I will try to hear it. I will speak to you about a new generation experiment for neutrino detection. I'm coming from the APC laboratory in Paris, and the name of the experiment is LBNO, which is Long Baseline Neutrino Observatory. So first of all, just let me just remind you some basics, the status of the knowledge of the neutrino theory today. So I will try to be to give you some information in a very simple way, but basically what we know today is that neutrinos are not massless as as the standard model says. So we have three neutrino families: electron neutrinos, muon neutrinos, tau neutrinos, and we know that the mass eigenstates and the flavor eigenstates are not the same. So basically, what you can do, you can manage to build a mixing matrix, such as in the quark sector, to pass from one flavor to the other. And this is described by three angles and two square mass differences and one complex phase, the CP. Actually, as the director was saying, this phase is, if it is not vanishing, it is responsible of the CP violation in the electronic sector, which is one of the most important items in the neutrino physics today. So the idea is that today what we know are the three angles and the two square masses. But what we don't know is the order of the mass of neutrinos. Of course, we don't know the absolute value, the value of each mass. We know just the difference. And as I said, we don't know the value of delta CP. So let me just spend 2 minutes to present you the activities in my laboratory for what concerns neutrinos. Of course, this laboratory APC is astroparticle cosmology. So the main items are astroparticle, of course, and cosmology, so Planck, etc. But there is a quite big neutrino group where we are involved in the double show experiment, which measured actually the theta 1,3 ion mixing angle in Laguna LBNO, which is my experiment, and I will speak about it soon. In the ORCA experiment, which is a sort of, if you want, upgrade or extension of the Antares experiment, which is an array installed in the Mediterranean Sea. Also, we are involved in the Boric-Sino experiment in Gran Sasso, detecting solar neutrinos. We are involved in the SOX, which is an upgrade of Boric-Sino to investigate the sterile neutrino hypothesis. And finally, we are involved in a new dark matter experiment in Gran Sasso, installed in Gran Sasso, which is called the GARSAT. So, the new generation experiments in the neutrino physics are very challenging because, of course, as you know, neutrinos interact very weakly with matter. So what you want is a huge detector mass, and the new accelerator-based, for example, accelerator. I will speak about it later. But for example, you want new accelerator-based neutrino beams. So you need a very broad collaboration. So the Laguna LBNO is addressing a very broad physics program, starting from accelerator-based neutrino physics to astrophysics and astronomy with neutrinos, of course, and finally geoneutrinos and dark matter. So I will just say. I'll just show you the main steps of this collaboration. So we start in 2008 with the Laguna design studies, which investigated the possibility to install a new detector, a new generation detector in Europe, investigating 7 sites and 3 different detector technologies. a liquid scintillator detector, a water Cherenkov detector, and a liquid argon detector. Then we pass, so basically what we did from 2008 up to today was just to select the good sites and the good detector technology, and to perform a detailed study, physics and design study. Today we are here basically. In September, we will start with the prototype of the detector, which is an experiment approved by CERN, which is named WA105, which is a small liquid double-phase liquid argon detector. So, the idea is to put a giant liquid argon detector, these two tanks here. Each tank is 65 meters diameter and 20 meters high, in the Piasalmi mine, which is a mine in Finland. So the distance from CERN will be 2,300 kilometers. This means that we will send a new neutrino flux generated at CERN through 2,300 kilometers of Earth in the detector installed inside the mine. In parallel to that, there is a second option, which is basically, probably it will not be done, but in any case, it has been studied in detail, which is a shorter baseline actually, from CERN to Fréjus Mountain at the border between Italy and France, which is a huge water Cherenkov detector. So these are two tanks of water. The total mass of this is 500 kilotons, and to detect a new neutrino flux from CERN to Fréjus, so 130 kilometers. So this is the scheme, the situation. So this is the baseline, the actual baseline. This is a scheme of the detector. The idea is to start with a 20 kiloton liquid argon detector and to go through an incremental approach, if you want, up to 70 kiloton liquid argon detector. And to do that, to do the experiment, we need a new beam, neutrino beam, which could be the 400 GeV SPS proton accelerator generated by that, or by an HPPS at CERN. So the idea, so this is a very, very schematic image of the tank, the detector. So the idea is that you have here some PMTs in the, on the floor of the detector. You have a cathode, you have an anode, so you have an electric field, a drift field. So when neutrino interacts, it produces charged particles such as muons or electrons. So if this is the muons moving inside the tank, it can ionize. So the ionization of the medium will produce a ionization charge, which will be accelerated through this electric field, and at the same time, the ionization light from excitation of the nuclei will trigger the acquisition. So these are some the basic elements. So the PMPs for light without. This grid is the extraction grid, because here it is liquid and here it is gas. Why we need gas? But this is just to, if you want to amplify the signal from the liquid phase. And there you have the charge result. So the beam is a quite conventional beam, just more powerful. So it is generated by 400 GeV protons. This is the idea, the spectrum we expect for the neutrino beam. In the red, you have, in the black, you have the neutrino, and in red, you have the antineutrinos. And what we do, so I will skip for the moment this idea of this history of maxima. I will come back later about that, but just to remind these two bands, green bands here for the moment. So what we are doing. So why, first of all, first question is why 2,300 kilometers? So what we want to do is to measure, as I said, the mass hierarchy of neutrinos, so to know which neutrino eigenstate is the heaviest, for example, so this will allow us to classify the free neutrino masses. So to do that, so the idea in this plot, I show on the x-axis there is the energy in gel. I'm sorry, okay. On the y-axis there is a probability, the oscillation probability. So you have, as a function of the energy, you have the probability for a muon neutrinos to interact as an electron neutrino, so to change its flavor. And as you can see, if we take the blue plot, for example, you have a maximum of probability here at low energies, and another maximum here about 4 GeV. So we call it the first oscillation maximum, and this is what we call the second oscillation maximum. And the blue is the case of the normal hierarchy. So for the hierarchy, we have two possibilities. M1, M2, M3, M3, M2, M1. So we call normal hierarchy the first one, inverted hierarchy the second one. And so if we put us at 2,300 kilometers, the situation is that you see a clear separation between the two possibilities at the first maximum. If we put us at the lower, shorter baselines, you see that this difference is not working. In that, what we expect to see is that, so we produce this kind of beam spectrum, and we expect to detect it in the detector, in the far detector, as that. So as you can see, this amount corresponds to the first maximum, this one, this region, and this little amount corresponds to this maximum. Of course, this peak is lower than this peak because of the low energies. So low energies cross-sections are suppressed, so it's more difficult to detect neutrinos in this inner energy region. So I show you rapidly the results of the simulation I performed. So what we do actually is to simulate these kind of interactions, evaluating the delta chi-square for different values of the delta CP phase. So excuse me, it's not clear enough. So what we do is to simulate the experiment, fixing all the parameters we know, and we keep free to vary the delta CP phase because it's the only parameter we don't know, and we evaluate the chi-square with respect to the model. So this is the results, the chi-square as a function of the model, but we can read the more simply, if you want, in this way, which means that if we want a 5 sigma confidence level of the results, Laguna and Beno can give us these results after about less than 2 years. So in less than 2 years, we can resolve the problem of mass hierarchy at 5 sigmas. Of course, as you can see, the 3 sigma confidence levels will arrive after some months, 6 months. Delta CP is, in a certain sense, is the same thing, but so this is the same spectrum you saw before, but I plot here different lines, color lines, corresponding to different values of delta CP. So the red one is for minus 90 degrees, etc. As you can see, the behavior is very different. So if we don't consider the 0 and the 180, because this means that CP is not violated, the 90 degrees effect is the blue, and the minus 90 is the red. And you see, this effect is very important here, but it's much more important here. The blue is there, and the red one is there. You can see it also in terms, this is in terms of energy, as before, but you can see it also in terms of L over E, where L is the baseline, the length of the baseline, and E is the energy. And here, the effect is much clearer. If you take a look at the green line and the purple line, you see that it's very, very important. So this plot proves, if you want, that a very long baseline is the only opportunity to get this kind of information. So these are the results in terms of for delta CP. So the idea is the same. So on the y-axis we have the delta chi-square. On the x-axis we have the true value of delta CP we are considering. So and this is kind of plot we read this kind of plot in this way. we cut it at the confidence level we want, so for example 90, 3 sigma, 5 sigma, etc. And we see how much of the phase space we can cover. So this plot, I propose you, I don't go in all the details. The difference of this these curves is just some differences in the assumptions, because we investigated in details the impact of the assumptions on the model. But the result, but I will give you the result at the end. Just another detail. I said before that we have two maxima. So the first one is very important because it's quite clear because we have a lot of events. The second is more difficult, but actually for delta CP we saw that the second maximum is the key point to get the measure. So if for example we cut here at low energy the spectrum and we perform the same analysis chi-square, you see that the results with all the information is the purple one, and without the second maximum is the red one. So we use a lot of sensitivity, and I skipped this, I don't have the time, but these are the results. So basically what we can perform today is that in maximum 10 years, we can cover more than the half of the phase space. Namely, we can cover basically 80% of the phase space of delta CP. So we can assure the measure of the delta CP phase if it is not vanishing. So let's just conclude. So the LBNO experiment is a new generation experiment which proposes in Europe a very challenging detector constructions to access to the last unknown parameters of the neutrino oscillation theory. To do that, we propose a double phase liquid atom detector starting from 20 kiloton up to 70 kiloton that in 10 years can perform the discovery. So now a prototype will start in September at CERN in the north area. This is the scheme of the prototype, the design. Then probably a 5 kiloton pilot will be installed in the mine just to start and see if this technology, we can control the technology overall. And then we will go from the 20 through the 70 kiloton. So, so okay, maybe this is not the only long baseline experiment in the world at the moment. This is the European proposal. So you will see, if you're interested in that, we can discuss later. You will now there are basically three ideas in the world. So the European is that. In Japan, the idea is to construct a giant water checkpoint detector. And a very similar experiment is proposed also in the US, which is named LBNE. But okay, actually at the moment, LBNO has just a very complete design. So if you want more details, just ask during the coffee break. Thank you.
Questions for Luca? Oh, I have questions.
Curiosity.
Okay.
So, what about the cost of such instruments?
Of course, yeah, the cost is a central point because it's huge. So, of course, a central part of the design, so I spoke about physics because, of course, it's more interesting, but the central part of the design is the reduction of costs, etc. So, today, the proposal, so let's say in an informal way, because the official paper document will go out at the end of the month, but is about 100 million euros for these options. This option, the first stage of the option, so the 20 kilo. But okay, so but the problem is that this is the same for all the three experiments. So yes, it's quite complicated.
More questions? I have one. In this kind of experiment which you described, which might be possible sources of systematics?
Yeah. So so basically, you have to you have to address basically two questions. One question is the knowledge of the beam, because of course you have to control exactly the shape of the spectrum which you want to investigate to oscillation maximum. And so if you want, this plot can answer the question, I mean, can just show you an idea, can give you an idea. So these lines are evaluated without systematics at all. This is for the 20 kiloton option. And the red one is the same with the systematic on the signal, so on the knowledge of the neutrino components on. So as you can see, it's very, very important. How to reduce it? But basically, the knowledge of cross sections, for example. So to have a near detector near the beam to measure the cross section of neutrinos will reduce this kind of problem. Yes. And the other side is the knowledge of the detector detection, which is another.
And so the plot that you showed before for the time of the reach 5 sigma, did that include
Yes,
the systematics?
yes.
Okay,
Yes.
so it's
Yeah,
amazing.
they are taken into account. And at this stage, I showed this kind of plot because they are published, but they are evaluated. So today, there been an update of the knowledge of the system. For example, on the errors on the oscillation parameter. So these are up to date, if you want, today. So today, the performances are better than that.
Okay. There are no more questions.
Just a curiosity. You told us that to reach the 5 sigma, you need 2 years maybe. Suppose you're lucky and this experiment will be approved tomorrow. How much time, in which year Europe would say to the world what is the hierarchy of things?
The answer is not simple because of course, okay, so let's suppose that there are no experiments in the world doing the same thing, because if you have other experiments you can merge just the results, so you can also, so if there are no experiments in the world doing the same thing, and if we have the money to build it, 2000, let's say 2022, something like that.
Okay, so we can thank Luca again.
Thank you.
So next speaker is Giancarlo Panizzo from University of Trieste, which will tell us about new physics signals from measurable polarization symmetries at LHC.
Can you hear me? Okay. This is actually my first time with a microphone. Okay. Okay, good morning. I'm Giancarlo Panizzo. I'm working here at Trieste, but at the university. My supervisors are Marina Kolbar, Professor Claudio Verzignassi, and I'm working with the Atlas Group, Udine Atlas Group, and IMFM, of course. In this talk, I will show you how polarization of symmetry at LHC can have an important role for physics in the next years. I will make a short introduction, especially in the theoretical framework. Then I will present the definition of the forward-backward polarization of symmetry at LHC, of the bottom work. And then I will talk about some experimental aspects of cosine diffraction. And also present a starting feasibility study of this kind of measure. Okay, let's talk about the definition. Since I know that maybe there are not much person here in this field, I will talk also about the simpler starting point of this measurement. Okay, so let's remember that two historical experiments in Europe that was SLC, the standard for linear collider, and also the LEP collider at CERN, measured already a polarization asymmetry of the bottom quark. That means try to think about collision of electron and proton, positron, sorry, and electron beams, and things try to imagine to produce in this collision bottom and anti-bottom pairs. Okay, since you are in the center of mass of these two beams, you know that the bottom and the anti-bottom will be back to back, and if you take as a reference frame the axis of the beam, you can define the angle between the beam direction and the jet, let's say, the bottom direction. Okay, so you can define a forward and a backward direction in some sense. Okay, so if you define the forward-backward polarization asymmetry at LEP or SLC as the difference of the two cross-section divided by the sum, I mean the production in which the bottom is forward with respect to the electron beam minus the production of the bottom in the backward direction, we have defined the forward-backward asymmetry at LEP. Okay? At tree level, in the standard model, you can easily connect this asymmetry to two asymmetry parameters that are related to the bottom and to the electron in this case. Okay, this is the formula in the standard model at tree level, of course, and you can see the definition of the asymmetry parameters. You see that they are defined as a function of the couplings of the fermions to the Z boson. Okay, so they are parameters that go to the heart of the standard model, that is its gauge structure. Okay, SLC measured a kind of different asymmetry, but it is you see that it is related only to the final states, and to be completely simple, to the asymmetry of the bottom quark. Okay, this is history. In the standard model, you can fit all the, let's say, observable that you can measure, and you can have a so-called global fit standard model. Okay. The interesting point here is that if you fit it, you can plot, as in this graph, the Q values. That is the difference of the measured value of the observable and the, let's say, prediction of your model, the standard model in this case, divided, of course, by the experimental error of the measure. Okay, if you do that, you will see that, in particular, the bottom sector presents some problems. That is, the forward-backward asymmetry I told you at LEP is the observable that is more discrepant in this graph. Okay, it is an old issue. There are a lot of articles talking about that. My approach here will be very pragmatic. Okay, that is, we don't know what is the source of this, let's say, Q value, high Q value. But for sure, we know from literature that no known models, not non-simple models, let's say, because there are models that explain it. But, for example, supersymmetric model does not explain such a high discrepancy. And it is funny that if you go into literature, you can see that, for example, the minimum supersymmetric standard model, or also the next to minimum supersymmetric standard model, has exactly the opposite contribution to this. Okay? So it is a puzzle for us. We will be very pragmatic, and we will assume, we will understand if there is a possibility to measure some observable connected to this one at LHC. Okay, this will be our approach. And this is the result of a paper we published the last 2 years. So at LHC, we have defined a forward-backward symmetry of the bottom quark, called here AFB at LHC, exactly in the same way as it was done at LEP. But remember that now you have you have different, of course, you have a different collider, because as you may know, at LHC you are colliding proton, okay? And so, for example, you don't know at LHC you cannot distinguish which one, since it is symmetric, because at LEP you knew that you had an electron in one side and a positive in the other. Okay? While at LHC you have two protons, so it is a symmetrical collider, so it is difficult to get asymmetries at LHC. This was the point of our definition. Because the point of our definition is go into associated production of a bottom and a Z boson. Here you see a bottom and a Z boson. Go into the rest frame of the Z boson, let it decay into lepton-anti-lepton pairs, and now if you are in the rest frame of the Z boson, you are going up to the LEP situation, because we have these axes, because in the rest frame of the Z boson you have the lepton and anti-lepton back to back, so you have the axis that was the beam axis at the LEP, and then you have this bottom here that that can be forward or backward with respect to this axis. Okay, so you can define also at LHC. We have shown that you can define this asymmetry, but here forward backward stands not for the beam collider, okay, but for the direction of the lepton anti-lepton pairs in the Z rest frame. Okay, we have shown that as you may expect at 3 level, this asymmetry at LHC is directly proportional to the forward-backward asymmetry of the bottom quark at LEP. Okay? This is a kinematical factor and can be computed by simulations or by calculations. Okay? So this was exactly what we needed. We want to measure another time these observables, and we have shown that LHC can have a role in this. Okay? Of course, you can ask that by only remember that to compute cross-section at LHC you have this formula. These are called PDFs. That's the parton distribution function of the different partons in the proton, in this case, and this is the partonic cross-section. This is a formula that you can, of course, find in literature in the known manuals. And the question is, okay, we defined a new observable, but how much it will be, what will be the errors associated to this observable, okay? The first error you can think as is the theoretical error, and in particular, the one coming from the parton distribution function, okay? So we have computed you see here, we have computed the associated error, the error associated to the parton distribution function, and in particular to the choice of the parton distribution function. And you can see that is for sure lower than 1%. We have tried to compute the influence of the renormalization and factorization scale to this observable, and we have shown that it is for sure lower than 1%. The error associated to the scale factorization and renormalization scales, let's say, that give us an idea of what could be the error associated to the next reading of the contribution. Okay? And also here you can see a plot that show the direct proportionality between the forward-backward asymmetry at LEP and the LHC forward-backward asymmetry. Okay, so from the point of view of the theoretical uncertainties, we are okay, because we have shown that they are for sure constrained lower than 1%. Okay. It is good defined. We can measure it. But from what happens if you try to understand what are the experimental errors, how much will be the precision that can be reached at LHC with such a measurement, such an observable. Remember that from CP symmetry, you will have for sure that the forward-backward symmetry of the bottom will be the opposite of the one of the anti-bottom. Okay, that was the problem I was trying to explain you at the beginning. Since LHC is a symmetric collider, and if you don't distinguish between the charges of the bottom and anti-bottom, you will find 0 for sure, because it is symmetric. Okay, but here the fact that this kind of observables were measured also at LEP help us, because we can use and adapt all the techniques to the new case. Okay, so our aim now is to understand if there is a possibility to distinguish between jet originating from a bottom and jets originating from an anti-bottom. Okay, it is very simple. It was used also at LEP. You can define, let's say, the charge of the jet, and you can define it in different ways, of course. The most simple is a weighted sum of the charges of the trucks inside the jet, weighted by a byte that here was chosen to be this byte. It uses some information about the trucks inside the jet. The trucks are exactly what you measure in a collision in the detector. Okay. Another way is to measure the charge of the muon detained from the bottom quark, and here you can see a strategy based with this receipt, let's say. So I've shown you two different ways to measure the charge of the jet, and these two ways can be put together and can be called charge of the jet. Don't think about which of the two methods. Okay, charge of the jet is that one. If in an ideal case, we can easily compute this charge with simulation, and let's define the mean of this distribution of the jet charge as delta B, and we can show, also using LEP technicalities, that the forward-backward charge that's defined in this way. This is a new definition for LHC. That's defined as the jet charge, I told 1 moment ago, multiplied event by a factor -1 to forward or backward. That means with +1 if the bottom is forward, or -1 if the bottom is backward. Okay, so you are writing the jet charge by this factor, event by event. So define the mean of this observable as a forward-backward charge, and you can see that it is experimentally connected to the definition of forward-backward symmetry of the bottom quark times this factor, this dilution factor. That's the mean of the charge in the case in which you have only a bottom, not an anti-bottom. Okay. In a non-pure sample, you have only to build this linear combination of the different patterns, these different fermions forward-backward symmetry, and with these factors that take into account the efficiencies and the cross-section of the different processes. In our simulation, we did a simulation to understand how precise will be this measurement, and we used the assumption of signal plus leading background from C-jets. So in this case, the formula is very simple. We've taken these factors delta B and C from simulation, but remember that they could be measured experimentally. For example, in 2 jets final state. This is a technicality, but it's only to remember you. And we have, of course, assumed the electron universality. The cuts were exactly the same one coming from the production cross-section analysis. So we have required a lower PT for the bottom jets. We have required this eta cuts. Also, we have required, of course, to have two isolated opposite charge electrons with this with this window in energy. Higher and lower than the Z mass. We have required a cut also on the PT of the electron and also on the observability. We have not restricted in any way the number of additional jets. And these are the results, let's say, of our simulation. First of all, the input parameters. These are the delta numbers that I was talking about. And they are taken from simulation, and you can take that from this table. This comes from simulation, okay? And we have simulated this kind of measurement in two different assumptions for the efficiency of the bottom course, okay? Of the bit tapping, sorry, of the bit tapping algorithm, so at 50% and 60%. And here are some numbers about the simulation. Well, here there are the results, times a factor of 10 to the fourth. So from this table, you can see in the two assumptions, you remember that I defined the charge of the jet in two ways, so with the weighted sum of the flux and also with the charge of the muon. Of course, these two measurements are independent because you are using a different part of your data, and so you can combine that, and the combined value has this kind of errors. This is not written here, maybe. Yes, it is written here at 3 inverse afterburn. No, sorry, this result is for 400 inverse 10 to burn at LHC. But these results, and for 400 inverse 10 to burn, you can see that more or less your relative precision is at the 10% level. But if you project these results at 3 inverse afterburn, that's 3000 inverse afterburn, you can see that from the point of view of statistical uncertainties, you can easily go down the 3% level. We have tried to understand what kind of systematic uncertainties can influence this measurement, and in particular, we have investigated the initial and final state radiation uncertainty, switching them off in the simulation and taking 20% of the total contribution. This is a result written in literature. We did not invest that. And we have seen that the final state radiation, that means the fact that maybe that in the final state you can produce additional jets coming from QCD, has negligible impact, while the initial state radiation gives an effect lower than 2%. Okay, the pile-up has no influence at all. We simulated 50 bunch crossing, and indeed that's a realistic level of pile-up at LHC. But we found that the effect is completely negligible. So we are at the conclusion, let's say, you have understood that at LHC, taking into account both statistical and the theoretical uncertainties, we can put an upper bound to the uncertainty related to these observables, okay? Because it was a simplified study, so you can expect that the uncertainty could be for sure lower than that. That is at 5% level. The net value of the forward backward bottom asymmetry is nowadays at 2%. So you can understand that this kind of accuracy, this upper bound on the accuracy, put this observable in a good place, because it can have a role in the world average of this of the forward backward asymmetry measurement. And of course, it will be very important, for example, in the global electrolyte fit that I showed you at the beginning. So, to summarize, remember that we have defined a new observable at LHC that's connected with the letter symmetry. We have checked the theoretical uncertainties related, connected to this observable, and we have found that it is a good definition because it has a very low dependence on the scale variations and of the set choice. We have completed a simplified, of course, a simplified feasibility study of its measurement, and we have set the upper bound on both the experiment, on the statistical and systematical uncertainties. And of course, the open question is if they will measure this observable at LC, in which direction the discrepancy will evolve, because you remember that supersymmetry does not explain this possible field value of the probable symmetry. I finished. Thank you very much.
Okay, any questions for Giancarlo? When you mentioned cuts, okay, because this is a technique when you have a lot of events, you need to select some events that you want to look at closer. So you want to reject everything else that is not interesting for you. How do you choose the cuts? And second, is there a fraction of interesting events that might possibly go into the cuts? Or, I mean, is there a contamination fraction? So you discard good events and you save bad events. So how important can this factor be?
Yes, first of all, the cuts has two reasons. One is technical reasons that your detector has some possibilities that you cannot go further. Okay. And so, for example, requiring a cut on the PT of the bottoms is not, especially in the rapidity. This issue is in the rapidity because you cannot cover the total angular distribution. Okay, so the rapidity more or less is connected to the angle at which you are producing your stuff. Okay, and so the cut on the rapidity is for that one. Why the cut on the PT? Is that because you want interesting events, and you understand that if your event has a boson, maybe negating the production, then the energy of your events will be higher than a lower bound. Okay, so this cut is for that reason. Of course, you have contamination, and in this simulation, how to choose the cut? You have to choose the cut to maximize the presence of the signal in your sample. Okay, but of course, no cut will be complete. Let's say you will not have, in any case, a 100% possibility of the signal and 0 from the background. So in this simulation, we took into account also this issue that's written. I don't remember where, maybe here. No, we took into account that factor. That means we took into account that there is a background. This was the definition of leading background. That's the background from the seed work. Okay, and in the simulation we added also this contribution, and this is the reason why at the end at 400% you have only 10% of accuracy, because we have the contamination of the seed.
So we can say that contamination accounts for 10% on the overall.
Yes, without contamination, you could have no, it's not 10%. Maybe it's 5% of the uncertainty. Without that contribution, you could have for sure a lower uncertainty on measurement.
Okay. Are there any more questions, Giancarlo? Okay. If not, we can thank him again. So this is the end of the first session. We have a coffee break waiting outside. And I would like to ask to some people, so Enrico Ubaldi, Laura, Ivan Del Vecchio, Laura Giacobetti, and Luca Agostino, if you could please go to Rossella, that is the girl with the black dress, and that is sitting back there. And Friedrich Schussler, if you can please come to us. Okay, so we will recombine like the CMB at 11:30. Please be sharp, and the coffee break is right outside here.